Hello, grade 10s, and welcome to Mindset Learn Extra. I go by the name of Pumi, and it is an exciting Tuesday because today we will be doing physical sciences with Tracy as usual. Now, guys, today we are going to be talking about a very interesting topic, and very excitingly so, we will be performing an experiment. I will be telling you a lot about it a little bit later on. But for now, Mindset Learn Extra, guys, is actually looking for new presenters. We have a new show coming up called Connections. So if you would love to be a presenter on Mindset Learn Extra, or rather on the show called Connections, all what you have to do is just to be here on at the Mindset Learn Extras studios on Thursday. For more information, please log on to our Facebook page, and then you'll find all of that and more posted for you. But right now, though, let me introduce you to our lovely teacher. It is Tracy. Hello, Tracy.
Hi, Pumi. How are you?
I'm very good, thanks. How are you doing?
Doing well, thanks. And grade 10's looking forward to the session.
Oh, yeah, absolutely. So, Tracy, what are we talking about today?
Today, we're going to be focusing on physical and chemical change. And it's a very interesting idea because what we're talking about is various different changes in matter that we see around us. So, has this thing undergone just a physical change, or has it been a whole chemical reaction? So lots of interesting thoughts to think about.
Oh, nice. So we really are performing an experiment?
We are indeed performing a few experiments because we want to look at the differences between physical and chemical changes. So yes, we are.
Oh, very interesting, guys. Please get all of your friends to actually come and watch the show because it is going to be very exciting. Remember, you can always post your questions on our Facebook page. It is www.facebook.com/learn extra. You can post all of your questions. We will answer them. Tracy, are you ready to take it away?
I'm ready. Thanks, Pumi. Grade 10, let's take it away. So we've got physical and chemical change, as we mentioned. Let's investigate what we're going to be looking at today. So what we will need to do is, specifically, we always have to define a new concept. And we will define physical and chemical change. And then, because these are two changes, we're going to need to compare them, and specifically compare the characteristics of physical and chemical change. And then once we're looking at chemical change itself, we will consider a few laws relating to chemical change. And then lastly, we will look at identifying whether something is a physical change or a chemical change. And always, we have to solve problems because grade 10, that's what you're going to be faced in a test or an exam. So won't you come across with me as we go and get started with some experiments. So come across to the board with me, to the table with me. I've got a few things set up here for you. Firstly, I've got a beaker with some ice. So that's solid water. Okay? And here I've got some hot water. And if you zoom in closely here, what you can actually see is that some of that steam that was rising as it was evaporating from this hot water has actually cooled and condensed on the side of the beaker. All right? Now I'm going to take the hot water and I'm going to pour it into the ice. And the question is, what do you think is going to happen? What do you think is going to happen? Well, what happens when you put something hot with some ice? Let's see. Well, there we go. The ice blocks are getting a lot smaller, and I'm just going to swirl that around a bit. Okay, and very clearly we can see that ice is melting. Now, I think I'm going to need to come back to this because it might take a bit of time. It wasn't boiling hot water. I could still hold the beaker. So we'll come back to this. But before we leave this, I want to think a little bit about this with you. Tell me, as I have the substance in here, what is it? What has something changed? What has changed? Is the stuff still water? What is the same and what is different? Well, certainly, there we are, much smaller little blocks of ice, because I know this is water. I don't mind taking it out. The little blocks of water, blocks of ice, I should say, have definitely gotten a lot smaller. What is different and what is the same? Well, we agree it's still the same stuff, okay? So this is an example of a physical change. it hasn't changed into a new substance. It's just simply changed the form that the substance is in. Okay, so it's still water. It's not a new substance, but it has certainly changed the energy that it has because we put something hot into something cold, changing the physical change, making a physical change. I could have put this over a Bunsen burner or in a kettle and boiled it. All right. Anything that's involving a temperature change, where you're just changing the state, will be an example of a physical change. Come across with me and let's have a look at some examples of chemical change. So in this small beaker, I now have a little bit of nitric acid, so an acid, along with some universal indicator. Now the universal indicator is that classic orangey color, and that is an indication to me that this stuff is an acid, right? I recognize that it's an acid because of that color of the universal indicator. And what I'm going to add into it is a small amount of ammonium hydroxide. So let's get a bit of ammonium hydroxide, and I want you to watch what's going to happen to the color. Okay. Immediately that's changed color. Let's add a bit more. And maybe we'll do a little bit more than that. And here, what you should see is it's gone from being that orange to almost a darker blue-purple type color. That is because as I add more of this ammonium hydroxide is a base. There we are. There's more of that purple color if you look closely. Okay. And what you can tell here is that this base is changing, reacting, neutralizing with the acid, and changing that into now a more basic solution. So what's happened is a chemical reaction. No longer do we have the acid in there. Okay, very important. The base has neutralized the acid, and actually because I've added it in excess, it's now a basic solution. So a big chemical change that has taken place. Now the last one, I've got some sugar, and I'm going to add some sulfuric acid, right? Now you might have seen this before. It's going to be quite exciting. So watch closely as we do this. And what you should see is we've got the color change that's going. It's now going almost a golden color, okay? And that golden color is an indication to me that a chemical change is taking place. The reason I say that, and now it's almost going black, and I can't get that sugar back. It has undergone a chemical change, and specifically what it's making is a carbon-based substance. So let's just trying to swirl this around. And we can tell that that sugar is no longer sugar. A new substance is formed. It's formed a carbon-based substance, and watch it as it goes. Rising up the tube, we've got some different gases that are formed here, but watch it as it goes. It's dehydrating, and so a lot of the water is coming out of that substance, but you can see this carbon is the black substance that I've got, and it's almost shooting right out the tube. Brilliant. Well, grade 10s, I really hope that that has shown you the difference between a physical change and a chemical change. Okay, so we've got a physical change, no new substance is formed, whereas a chemical change, a completely new substance has formed. Let's go back across to the board. Won't you join me there? So grade 10s, we've done our demonstration, and now let's get into the ideas around physical and chemical change, specifically as we look into the definitions of each. So let's go with physical change. A physical change can be seen or felt. So there is a change that's happening, but it doesn't involve the breakup of the particles in the reaction. During a physical change, the form of matter may change, and by form, I mean here the phase or the state of matter may change, but not its identity. So the substance itself does not change. It's not changing into a different thing, okay? Still the same substance. For example, water can change its phase from going from solid to liquid to gas, but it has not undergone a chemical reaction. The water particles are still water particles. They're still that same H2O. What has changed? Well, maybe the temperature and the energy of the particles has increased as you have put energy in. Okay, so here I've got a model of some liquid water and some gaseous water. The liquid, we can see those particles are closer together. We can see those particles are able to slide over one another. But what are they made of? Well, we've got an oxygen and a hydrogen. Okay, and on this side, what have we got? Still an oxygen and, I shouldn't say a hydrogen, two hydrogens. The same substance, what has changed? Well, they've moved apart from one another. They're slightly further apart. Some other examples of physical change would be conduction, the transfer of energy through a material. If you heat up one side and allow energy to be transferred from one to the other. If energy is transferred from one material to another, the energy of each material is changed, but not its chemical makeup. And I think that word, those words, chemical makeup, really do refer significantly to what we've got. And then the last one, dissolving a substance into one another. So if you've got maybe some sugar dissolved in water, it still tastes sweet, it's still got the sugar in it, it hasn't changed. For me, I think we should take an ad break after that exciting chemical reaction. Over to you.
Oh, thank you so much. Guys, please do remember that if you have to perform an experiment, be sure that you have an adult to help you out with that and wear your protective clothes. Right now, I beg your pardon. Right now, though, let's take a quick break. We'll be back after this. And welcome back, guys, from an ad break. You are still watching Mindset Learn Extra. We are doing physical science, and if you just joined us, you must have just missed the experiment a little. But don't worry, guys, because Tracy is going to be doing the theory with us, and it's so interesting. So, Tracy, can you quickly remind us what we're talking about today?
Thanks, Pumi. Absolutely. So, grade 10, we're looking at physical and chemical change, and we just looked at some experiments, and we're about to get stuck into chemical change specifically.
Oh, awesome, awesome. It is just like that, guys. Remember, Mindset Learn Extra is actually looking for new presenters. The name of the show that we're looking for, the name of the show that Mindset is actually having is called Connections. So for all the details, in order for you to come and audition and everything like that, please log on to our Facebook page. Our Facebook page is www.facebook.com/learnextra. Guys, remember, you can always enter the Future Stars Awards. It's still open for you, so please do enter it in order for you to win cool prizes with regards to the awards. In any case, Tracy, let's do this.
Thanks so much, Pumi. Grade 10, we've just looked at physical change in detail. Now let's look at chemical change and what we expect by chemical change. So chemical change, when a chemical change takes place, new substances are formed, and that is critical, okay, in a chemical reaction. These new products may have very different properties. So, for example, if I think about little iron filings with some sulfur. Iron filings have a property of magnetism. They can be attracted to a magnet. Okay, so, and the sulfur doesn't. But if we mix those two together and we just have them as a mixture, I could separate the iron filings from the sulfur take them out, okay, using a magnet. But if I undergo a chemical reaction by heating that iron sulfide, it now forms that's iron sulfur mixture. It will form iron sulfide, which is a completely new substance and does not have any of those chemical properties of magnetism. So notice the new products may have very different properties from the substances that were there at the start of the reaction. One type of matter is changed into something else, something different. Now what I've got for you is a PhET simulation, and grade 10s, remember, you can go and download these notes, you can go and check them out, and you can go and play with these simulations. So if I go across here, I've got a game that I'm going to play with you, and what it's saying to me is this is a real reaction. This is actually called the Haber process, and what it is it's ammonia, it's forming ammonia. So it starts with nitrogen gas, and hydrogen gas, and it forms NH3, which is ammonia. And what I want you to look at, I can change the numbers on the screen, okay? So you can see this, go back down to naught. I can change the numbers on the screen. And let's go down to naught. And what you find here is what I have before, and there is after. So let's have one nitrogen, only one. Okay, that's the blue. Notice it's diatomic, which means di means two, atomic atoms. So two atoms joined together. Hydrogen, I want to have three of them. And notice there, the white ones, they also are diatomic. And what they have formed is something completely different. Those two nitrogen atoms separated, broke apart, okay, as well as those three hydrogen molecules with their diatomic atoms broke apart, and they have formed these two ammonia molecules, right? Let's go across and let's try and make some water. So what have we got? Some hydrogen, and I'm going to play and let's get a water, and there we have a similar so an oxygen diatomic, hydrogen diatomic, they break apart and they form two water molecules. Something that was at the start has formed into something completely different, right? It's a chemical reaction. Coming back to our notes, one type of substance is changed into something different. Let's go through some examples. Now, I thought there were two important words that I wanted you to come across, and that is decomposition and synthesis. Okay? Now, to decompose, if you think biology, a decomposer is at the end of the food chain breaking things down. Okay? To decompose is to break down, right? So decomposition, the breaking down of hydrogen peroxide, is one of the reactions we will look at. It's a chemical reaction. Synthesis is another key word I want you to note. To synthesize would be to put together or to form. All right? So photosynthesis would be what plants are able to do when they use raw materials, carbon dioxide and water, and put them together to form a carbohydrate using the sun's energy. Okay? So two important words, decomposition and synthesis. You need to know what they mean. Decomposition means to break down. Synthesis would be to form. So let's look at decomposition. The decomposition or breaking down of hydrogen peroxide. Hydrogen peroxide has that H2O2 formula to form water. So that's one of the products, as well as oxygen. This is an example of a chemical change. So what we've got at the start, these are our reactants, and these things on this side are our products. Okay? Notice two hydrogens, two oxygens, two hydrogens, two oxygens, forming H2O and another H2O and an O2, oxygen. Another one, we said we were looking at synthesis as well, is the forming of water. So to come together to make something new, the formation of water from hydrogen gas and oxygen gas in order to make water. is another example of a chemical change. The chemical bonds are broken and new bonds are formed. So having a look at this one, here we've got an oxygen that's diatomic, O2, all right? And the bond that is between those two oxygen atoms has to separate in order to make two water molecules, right? So old bonds need to break and then new bonds need to form. Similarly, the little bond, let's change color and indicate those little bonds there. The little bonds between hydrogens need to break and so that they can bond with the oxygens individually. Notice old bonds break, new bonds form. A new substance is then formed, a chemical reaction. What I decided to do as we were preparing for this is to make sure that we can compare these two things very well, physical change and a chemical change. So I've put this table together, and what we've got is we're going to look at these two, a physical change and a chemical change, under certain categories, right? So tell me about the arrangement of the particles, or tell me about energy change, or tell me about reversibility, okay? So we're comparing in the first, so this middle column I've got physical change, and the last column chemical change. Now, when we speak about arrangement of particles, I want to say, like, how are they situated? What is the arrangement? So for a physical change, compounds may rearrange themselves, but the bonds in between the atoms will not break, okay? So the H2O, as we had there, was solid H2O, and then it separated into becoming liquid, able to flow over one another. But the H2O particles stayed H2O particles. They didn't break apart. Their identity stayed the same. They were just able to rearrange. Whereas during a chemical change, the particles themselves are changed in some way. As we saw, the hydrogen peroxide changed into something different. If we go for conservation of mass, we'll talk about this one quite a bit more in our next segment as well. For a physical change, the total mass, the number of atoms, and the number of molecules always is the same, stays the same. So when I say conservation, we're talking about conserve the rhinos or conserve our ecosystems. We want them to stay as they are, okay? We want them to be there for future generations, all that kind of thing, all right? Very important. Conservation, meaning to stay the same. So the idea with conservation of mass is that there are still the same number of particles, okay? Or sorry, I should say still the same mass. For physical change, the number of molecules will always stay the same. So if I started with 3 water molecules, imagine on a tiny scale, if I started with 3 water molecules and I was just able to give them some heat and separate them a bit, there will still be 3 water molecules. They're not going to change, they're just moving away from each other, okay, slightly. Whereas with a chemical change, mass is still conserved, but the number of molecules may change. So let's have a look at one of the examples we considered, the decomposition of hydrogen peroxide. And I want us to go back to it. We had it on the previous page. Let's jump down to it. This is the one we had. I have 2 of these H2O2 molecules, right? So I started with 2 molecules. What do I end up with? 1, 2, 3. 3 molecules at the end. Well, firstly, we can say definitely 2 molecules went to 3 molecules. The number of molecules changed, but notice they broke up and they became smaller molecules. So the number of molecules didn't stay the same, but actually the mass of this thing has stayed the same. Why do I know that? Well, because let's count with me quickly. How many oxygens did I start with? 1, 2, 3, 4. And I ended up with 1, 2, 3, 4. I still have 4 oxygen atoms, okay? And the hydrogens, 1, 2, 3, 4, 1, 2, 3, 4. I've still got the same number of all the substances that I had. So their mass is conserved, but the molecules have changed. Come across, and we'll finish off that note. So we said, in the example of hydrogen peroxide, for every 2 molecules of the hydrogen peroxide that decomposes, 3 molecules are formed, 2 water and 1 oxygen. And we can tell that the mass is conserved, but the number of molecules may change. Okay, the number of the things I have may change. Let's go through some energy discussions now. Energy changes. Energy changes for physical changes are normally smaller than energy changes that take place during a chemical change. For chemical changes, they are usually much greater in a chemical change than those that take place during a physical change. And the question that I'm sure you want to ask is, why? Why? Well, during a chemical reaction, energy is used up in order to break the bonds, and then energy is released when a new product is formed. Okay? So what you've got is these molecules breaking apart, atoms rearranging, bonding with something different, and then releasing energy as they bond. And so what we can see is quite significant energy changes during a chemical reaction. And you'll learn about an endothermic reaction where more energy is taken in, or an exothermic reaction where more energy is taken out or given out. Okay? So significant energy changes can take place with chemical reactions. The last one to consider is reversibility. Okay? Now, reversibility, physical changes in matter are usually much easier to reverse than a chemical change. So let's talk about dissolving something. If I take some sugar and dissolve it in, or salt and dissolve it in water, right? How could I get the salt out of that water? Reverse that physical change. Well, I could leave it in a sunny spot and allow the water to evaporate. Or maybe if I've got some sand in water, I could filter that out. Another way, if I wanted the water, not the salt, well, you could go through a distillation process where you heat it and then allow the water to cool and condense and drip back down. Okay? So all of these processes are quite simple to go through, and are relatively simple to reverse the process for physical changes. Whereas for chemical changes, they are far more difficult to reverse than physical changes. It is possible to reverse them, but they are a lot more difficult to reverse. Some reactions are impossible to reverse. Some reactions, or I shouldn't maybe say impossible, but would take a large number of steps in order to reverse. Okay? Whereas other reactions reverse by themselves naturally. Okay? So a large number of different options. Pumi, I think we should probably take a break. I've loaded you with a whole bunch of new concepts. So grade 10s, take a short break. Over to you.
Yes, guys, please take that short break. We'll see you after this. And welcome back, guys, from an ad break. Remember, guys, you are still listening to Mindset Learn Extra right here on your DSTV channel 319. I'm Pumi, and I'm in studio with Tracy. And yes, we are still talking about, what are you talking about, Tracy?
So we're going to finish off with some more physical and chemical change, and specifically what we're going to be looking at is rounding off the laws, so a few laws that you're going to need to come across, and we'll answer some questions. Okay, so grade 10s, make sure that you've got these, that you sorted, and these laws, particularly the first two, are incredibly important. We can ask lots of questions on them. But you need to also be able to identify physical and chemical change, right? So remember, physical change, something that can be seen or felt, but the particles themselves are just simply rearranged. They are not changed into something different. Whereas a chemical change is something completely changing into a different substance, a new substance that is being formed, right? And you need to be able to identify the difference between them. So let's go through a few laws. We are focused now on chemical change specifically, and a few laws that relate to chemical change. We already have the law of conservation of mass, okay? And mass is a measure of the, sorry, this pen is not playing the game with me, is an amount of matter. Okay? So here what we are focused on is that matter is not created or destroyed. It's still there. It's just been rearranged, right? So in a chemical reaction, the total mass, the total meaning the sum, okay, altogether, the total mass of all the substances taking part in the reaction remains the same. Also, the number of atoms in a reaction remains the same. Mass cannot be created or destroyed in a chemical reaction. And that idea of the number of atoms is very helpful. Remember right at the just in the previous section, we were talking about hydrogen peroxide decomposing, and we had counted out the oxygens and we counted out the hydrogens, and we found that they were the same on either side of the reaction, okay, at the beginning and at the end. And it's the same with the amount of matter, okay, the mass of these things. So notice this is the law of conservation of mass, okay? You need to know it. It's a very important one. And the title gives it to you. It's a law, the conservation of mass. What are you conserving? Conserve means to remain the same. So the idea is the total mass of all the substances remains the same. A number of atoms remains the same on the left-hand side and on the right-hand side, or in the reactants and in the products. Right. The next one, the law of constant composition. So once again, we've got a law. You need to know it. In any given chemical compound, so this is now within a chemical compound, okay? The elements always come together in the same proportion with each other. For example, in any water is always made up of 2 hydrogen atoms and 1 oxygen atom in a 2:1 ratio. And so immediately if you speak about a water molecule, you think H2O. Because the law of constant composition says that for water, it's going to be 2 hydrogens for every 1 oxygen. So H2O in a 2:1 ratio. For ammonia, it's going to be NH3, a 1:3 ratio. For all those different substances have a law of constant composition, okay? The idea that in a chemical compound, elements combine in the same proportion. And the last one is one we don't often hear about, but I thought I'd include it anyway so that your notes are complete. The Gay-Lussac law. In a chemical reaction between gases, okay, the relative volumes of the gases in the reaction are present in a ratio of small whole numbers if all the gases are at the same temperature and at the same pressure, okay? Well, why? Because for a gas, imagine if you increase the temperature, then this thing's going to expand, all right? If you increase the pressure, then what you're thinking of the particles will be more tightly packed, okay, and be hitting against the sides significantly further. And so temperature and pressure can have a significant impact on the number of particles, the properties of a gas, okay? We'll go into that more in grade 11 and further on in your course. But what I want you to think about here is if you've got a volume of oxygen and a volume of hydrogen, right? Those two gases, if they're at the same temperature and pressure, okay, then in order to make water, what will you need? You would need twice as much hydrogen as to the oxygen, because what you're forming is in a 2:1 ratio, right? Let's have a look at this. For example, let's move our page down. In the reaction between hydrogen and oxygen, to produce water, 2 volumes of H2 react with 1 volume of O2 to produce how many? Well, it will produce 2 volumes of H2O. We haven't looked into balancing equations yet, but what I want you to notice is that this oxygen is diatomic, okay, which means it's got an O2. Similarly, that one, H2, it means two oxygen atoms or two hydrogen atoms joined together. So when you react them, you need to have 2 volumes of the hydrogen for every 1 volume of oxygen, and you're going to produce 2 volumes of water. Now, we don't look significantly into this law, unfortunately, but hopefully that gives you just a bit more of clarity. Let's go on to some questions, because I know you're dying to always be able to answer questions, and this is what you will be faced with in a test or an exam. Question 1. Complete the following table by identifying each of the descriptions as an example of a physical or chemical change. So let's get ourselves going, and what we're going to do for each of these questions is write in, is it a physical or chemical change? So hot and cold water mixed together. Well, hot and cold water, that's going to be a temperature change that's going to take place. Is this going to form a new substance? I don't think so. It's going to still be water. It's just going to now be a lukewarm water if you've added the two. And so it will be a physical change. A car starts to rust. Now, what does rusting mean? Rust is iron oxide that's formed, okay? And so that's going to be the metal of the car reacting with oxygen in the air, right? And oxidizing to form rust. So, is that a new substance that's forming? Yes, it is. It is a chemical change. Food digesting in the stomach. Well, that's also going to be a chemical change, because if you eat a bite of your hamburger or whatever it is, that food starts to break down into small pieces, or very small pieces when you've chewed it, and then very, very tiny pieces in order to be absorbed into the bloodstream so that you can transport those nutrients around your body. So in the stomach, it's going to be digested and broken down into very, very tiny pieces, into what we call the amino acids and the small little units that it will be absorbed by your into the bloodstream. So is that a physical change or a chemical change? It's going to be a chemical change, because it's forming a new substance. Now, if I had to spill a bit of alcohol on your skin, okay, now maybe it's a little bit of methylated spirits on your skin, what's going to happen? Well, surely it would quickly evaporate. You know, alcohol is highly volatile and will evaporate very quickly. Is that a physical change or a chemical change? You could probably still smell that little bit of alcohol in the air, and that would be a physical change. It's gone from liquid into a gaseous state. So it's a physical change. And then fireworks exploding. Fireworks packed full of chemicals, and as they react, that would be a chemical change. Now let's get on to one more question. And as we tackle this, it's quite a long question. For the following equation, calcium carbonate, this stuff, forms calcium oxide plus carbon dioxide. Show that the law of conservation of mass applies. So we've got to go back and say, what is the law of conservation of mass? The law of conservation of mass says that the total mass of the system remains constant. Okay? So what you have is everything in the reactants must be the same as everything in the products in terms of their mass. Nothing's been created or destroyed. So what I'm going to do when I tackle this question is I'm going to draw a little dotted line down my page, just in pencil, very lightly. And on this side I've got the calcium carbonate. And on this side I've got the calcium oxide and the carbon dioxide. Okay? This on the left, this is going to be my reactant. And on the right, these are my products. Okay, there are 2 of them, but that's absolutely fine. Now what I want us to tackle is this in terms of its mass. So I'm going to write here mass. What have I got at the beginning? I have got calcium carbonate. And I want to work out what the mass of the substance will be. For that, I need a periodic table. So as I look here, I've got a periodic table. You would need to go and find this. Maybe it's the front of your textbook or the back of your textbook. You've got a periodic table to reference. And I'm showing this to you specifically because I know that you need to be able to refer back to it and find the information where the information for everything is. So I have calcium. Now let's circle calcium. I want to show you. There's the calcium, right? I want oxygen. I want carbon. Okay? Calcium carbonate, right? Now, for the calcium, what is its mass? Your periodic table always has a legend on it, right? And you need to go and look at what the legend, the little key on the periodic table will tell you, right? Because periodic tables are laid out differently. So this one at the bottom, I'm told, is the approximate relative atomic mass. So the number there is going to be the mass number. So for calcium, it's 40. Let's go back and write that one in. What have we got? We've got calcium is 40. Okay. Carbon, for carbon, some people like to put these in brackets. So let's go with the brackets. Let's change color. Carbon, the 12, and oxygen is 16. Now, let's go back, and we've got those numbers. So carbon was 12, and I've got how many oxygens? Now, 3 oxygens. The number was 16 for the mass of 1 oxygen atom, but have a look here. I had a carbonate, so calcium carbonate, and that was with 3 oxygens. So let's just do a bit of quick maths here. And we've got, sorry, I changed my pen color. We've got 40 plus 12 plus 3 times 16, and I've got my calculator, because I'm sure you will do this on your calculator. I always start with the multiplying first. 16 times 3 is equal to 48, but I've got to add in the 12, and I've got to add in the 40, and we come to 100. Lovely little round number. So we'll go back and write in 100, and if you want to unit, atomic mass units should be fine. Okay, so that is my left-hand side, if you like, the reactants. The products, well, for my products, what we've got would be the mass of calcium oxide as well as the mass of carbon dioxide. Let's take each of these. Well, for calcium oxide, calcium, go back to the periodic table. There it is. Calcium, it's a group 2, okay, and its mass was 40, and oxygen, its mass was 16. So let's go and write those in. This one was equal to 40, if you want in brackets, plus 16, plus the mass of carbon dioxide. Carbon, I recall, was 12. And there were how many oxygens? Well, it's 2 times the 16. So finishing this off, 40 plus 16 will be 56. And I must add in 2 times 16 is going to be 32 plus 12. So let's go back and just quickly clear that. It was 32 plus 12 plus, I think it was 56. Should we just check it quickly? 56, 12, 32, I think we've got it. Okay, equals 100. Fabulous. So I go back, and what I have done, atomic mass units, and what I have done is proved that the left-hand side and the right-hand side have the same mass, okay? The mass of the reactants is equal to the mass of the products. Now remember, if they've asked you to prove that, you can't assume that, okay? You've got to show them separately and show that they're equal at the end. So grade 10s, I really hope that's helped you as you work through physical change and chemical change. Recall, physical change can be seen or felt, but it's only the rearrangement of the particles. They haven't changed into anything new. Whereas chemical change is where you have the idea that a new substance is formed, right? And then we work through those laws. You must make sure that you're able to tackle each of those. Grade 10s, I hope that's really helped you. Keep well and God bless. I'll see you next week.
Thank you so much, Tracy. That was a very interesting lesson today. Remember, guys, if you just joined us now, well, you know what, don't worry, because we performed an experiment. So if you want to see what happened, please, or rather, if you think that you missed it, please ask your teachers at school to repeat it for you. Remember, you can't do it alone. Wear your safety gear. But in any case, guys, Connections right here is looking for presenters. It's a very new and exciting show, and it's a talk show that is. So all what you have to do is just to be here and get yourselves auditioned on Thursday. So guys, remember that you can you have to also have your own transport in order for you to get here and everything like that. In any case, guys, it was very exciting to be having you on the show today. Remember, thank you so much, guys, for coming, or rather listening. Oh, sorry. Thank you so much, guys, for actually watching the show. It's been really great having you with us. But for me, Pumi, it is bye-bye.